Welcome to the third part of Unit 9. In this part, we're going to introduce the law of universal gravitation. The law of universal gravitation governs the force of gravity between any two massive objects. It could be the sun and the earth. It could be the earth and the moon. It could be between me and my microphone. Any two objects with mass. The form of the law of universal gravitation, I use F sub g, is given by g times the two masses, m1 and m2, divided by the distance between them squared. So if I draw a picture, I have one object, I have a second object, and I have them separated by a distance. If this were the Earth and that the moon, this r would be the radius of the moon's orbit, for example. G is a constant, and it has a value of 6.6, times 10 to the minus 11. Ooh, that's not a very good 11. Let's try again. Negative 11 Newton meters squared per kilogram squared. Now, let's pause for a minute before we move on and just toss some numbers into this formula. It's the time of social distancing. So let's assume that these are two adult humans and you're 6 feet, which is roughly 2 meters apart. If I calculate that force, I get 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times 60 kilograms times 60 kilograms divided by 2 meters squared. And if you put that all into a calculator, 6.67 times 10 to the negative 11 times 60 divided by 2 squared, you get 6 times 10 to the negative 8 newtons. So between everyday objects, two people, myself and my microphone, this is a very, 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 very small force. There are experiments you can do which demonstrate it. A common one is known as the Cavendish experiment. But in general, you don't notice it because other forces in your life are so much bigger. Okay? Or have the potential to be so much bigger, like friction. We can see on Earth examples of the gravitational force between the Earth and the moon. We know that the gravitational force is the reason that the moon orbits the Earth. The moon's effect on the Earth, so the third law of force pair of the Earth on the moon, if you will, is apparent in tides. So we're going to go look at a simulation for tides. Now, regrettably, this simulation is a flash simulation, which means, at least on my computer, it only runs in Internet Explorer. So it looks like this. Okay, so right now you can see the Earth, you can see the moon up here, and you can see the tidal bulges. On the side of the Earth nearest the moon, the water bulges outward because it has a stronger gravitational force and therefore is pulled towards the moon. On the side opposite, you can also see that the water is bulging outward. And the reason for that is because it's further away from the moon, therefore it has a smaller gravitational force. And you can actually calculate the difference in the gravitational force due to the moon being on the near side of the Earth versus the far side of the Earth. If I click run, you'll see the moon start orbiting the Earth. The Earth is spinning on its axis, and the tidal bulges follow the moon in its orbit, right? So if I drew a straight line that went from the moon to the Earth, those tidal bulges would just line up right on that straight line. Notice that as the Earth spins, it moves under each of the two bulges each day, which means we have 2 high tides and 2 low tides each day. Also notice that we spin lots and lots of times around in the time it takes for the moon to complete one orbit. Well, remember, the Earth spins on its axis once per day. The moon orbits the Earth once roughly every 28 days. It's once a month is a good rule of thumb. It's not quite true, but close. Okay, well, this isn't all of the story because the moon isn't the only object that's out there. So let's add in the sun and see what effect that has. So the sun is off screen somewhere here to the right. And if you watch, when the moon is perpendicular to the direction from the sun, which it's approaching now, so you got the sun this way and the moon is below. See how the bulges even out and you get high tides that are not much different from your low tides. But when the Earth or when the sun and the moon are both in the same direction, you get very large high tides compared to your low tides. And it goes through this cycle. Okay. This is a question of, are the gravitational forces from the moon and the sun working together, or working against each other, or even perpendicular to each other? Okay. But still, as we watch this, you can see that the line between the moon and the Earth still pretty much dictates where the high tides are going to be. But again, that's not the entire story, because the Earth is rotating. And if you think about something that is rotating, it pushes the liquid in front of it. So think about the blades in your blender and how the liquid in your blender moves in front of the blades, and you get this bulge in front. So if you include the Earth's rotation, I'm going to let go of the sun for a minute so I can include this more easily. You can see that the line for the high tides no longer lines up perfectly with where the moon is. And that's because the water is getting pushed in front of the Earth as the Earth rotates. If I now put the sun back in, you again get big tides when everything is lined up, and smaller tides when everything is, or when they're perpendicular to each other, if you will. Okay. So that concludes our look at tides. It also concludes this part of Unit 9. In the next part, we will again do calculations and examples.